Good morning, everyone. I'm a second-year PhD student working with Paul Fiddler and James Talbot here in the CSIC, and continuing the theme of sensor-based continuous condition monitoring, I'm going to show you some signal processing techniques that extract useful information from an accelerometer signal that is otherwise of limited use on its own. So, I am developing these techniques to monitor the roughness of railway tracks using sensors on passenger trains, that's accelerometers on the axle boxes. So why am I doing this? The roughness of railway tracks increases over time due to wear from trains, and this typically occurs at wavelengths from 3 centimetres to 2 metres. Sometimes this wavy pattern appears in the railhead, which is called corrugation. This is a problem for rail operators because corrugated rails create high levels of noise and vibration, which is a nuisance to people living near the railway, as well as damaging trains. As you can see in this diagram, noise can propagate through the ground and re-radiate inside buildings. Many metro networks, including the London Underground, are dealing with corrugated rails and ground-borne noise. So currently, the railways are manually inspected for high levels of roughness, such as by using dedicated measurement trains. But this tends to be costly and time-consuming. So I'm proposing a more efficient method, which is to use sensors on in-service trains, as I said previously. There are sensors that directly measure rail roughness, such as by physical contact or lasers, but these tend to be fragile and awkward to maintain, so they're not suitable for in-service trains. Instead, accelerometers are more suitable because they are maintenance-free, practically, and we fit one of these accelerometers onto a part of the train's bogie called the axle box, and we call it an axle box accelerometer, or ABBA, not to be confused with the band. So ABBA measures vibration caused by rail roughness rather than the roughness itself. So it requires signal processing techniques to derive the roughness from the ABBA measurements. We have collected measurements from a trial system on one of the West Midlands Metro trams. This is a CAF Urbos 3 tram, and it has independent wheels connected across by axle beams to enable a low-floor design. And we fitted 5 accelerometers, 4 on the front power bogie and 1 on the trailer bogie. This shows one of the axle beams, and this is one of the accelerometers attached to the beam near the wheel bearing. Now I will show you measurements from the system, which covers the West Midlands Metro network from Wolverhampton to Birmingham. This graph shows the root mean square, or RMS, of ABBA. From Wolverhampton to the middle of the network over 50-metre segments. And it shows data from April 2017 to October 2018, heading down the colour spectrum, and the symbols here show where the stations are. In mid-2017, the track between the Rail and Priestfield was very rough, but it was replaced in December that year, and you can see the big difference in RMS levels here. Now, these measurements don't quantify rail roughness by themselves, so they need some signal processing techniques to derive rail roughness from ABBA, which is what rail operators would like to measure. Rail roughness is connected to ABBA through the dynamic train track system. This is a diagram of the train track system, which has a wheel and track with a roughness profile moving between the wheel and rail and exciting vibrations in the system. We are measuring ABBA, which I'm assuming is the vertical acceleration of the wheel. The key point here is that the measurement depends not only on rail roughness, but also on the system itself. So we need to know the system in order to derive rail roughness from ABBA. I can represent the system as a transfer function, h of omega, and if we treat, this graph shows what h of omega might look like. And to get rail roughness, or if we treat rail roughness as random processes, then the PSD of rail roughness is multiplied by the square of the transfer function to get the PSD of ABBA. Now we can derive the roughness by simply inverting this transfer function, but we want the roughness in the fixed reference frame rather than from the train's point of view. So we translate it into the wave number domain. And for those who don't know, wave number is the number of oscillations, radians of oscillation per meter rather than per second. So that removes the dependence on the train motion. This leads us to the final equation. And for completeness, wavelength is 2 pi over wave number. So the roughness PSD shows the amounts of roughness at each wavelength that is independent of the transfer function and the train speed, and which will be useful for rail operators to optimize track maintenance schedules. I'll just go into some more detail on how we calculate the power spectral density of the ABBA signal AFT. We use the square magnitude Fourier transform, which we call the periodogram, and we apply a window function to the signal before taking the Fourier transform. Now, the statistical accuracy of a periodogram is very coarse. As you can see, this spectrum is very noisy. So how do I improve the accuracy? One way is to average together periodograms of multiple segments of the signal, which is essentially Welch's method. This method splits the tracks in the signal into several segments, which are overlapped with each other, and a hand window is applied to each segment. And I use 30 segments in total to improve the statistical accuracy, and this makes the spectrum much smoother. Now, improving the accuracy trades off the resolution of the spectrum, and this trade-off depends on the requirements of the system. For our work, we've used the standard EN 15610, which is commonly used by in industry and by researchers to plot rail roughness spectra. It recommends a spatial resolution, or total track length of 60 times the maximum wavelength, and a segment length of 4 times. So that's why we chose 30 segments. This diagram shows how the wavelength, segment length, and spatial resolution are correlated with each other. And the standard specifies wavelengths up to 0.25 meters, but actually corrugation can occur at longer wavelengths as well. And ground-borne noise is also relevant at these longer wavelengths. So we chose to increase that to 1 meters, which gives this segment length and spatial resolution. The same standard also recommends plotting the roughness as third octave spectra like this. I wonder if you've seen a third octave spectrum before. You can see on the wavelength axis that the wavelength doubles every 3 bands. The y-axis is in decibels relative to 1 micrometers, so 0 decibels is an RMS amplitude of 1 micrometers. This particular spectrum is the limit spectrum for the roughness of a section of test track that is used to type test new rail vehicles, and it's given in this standard, ISO 3095. But it's a useful spectrum because it's close to the typical roughness of railway track. So we use this spectrum in our simulations. We have developed a theoretical simulator to test and evaluate the techniques to derive the roughness from ABBA. The simulator uses a time domain model, which is based on a beam on elastic foundation to represent the track and a lumped mass to represent the unsprung mass of the train. This may appear oversimplified, but the wheel mass is essentially decoupled from the rest of the train by the soft primary suspension. The simulator calculates an ABBA signal given a rail roughness spectrum and the parameters of the system. And I chose the ISO 3095 spectrum, but with a sine wave peak added to represent corrugation. And I generate a random profile for the simulator. Suppose that the train is stopped at a station on the left, and now it is accelerating, and we're recording the ABBA signal arising from the roughness on the track, along with the train speed. And as you can see, the signal is very low when the train is slow, but as it speeds up, the magnitude increases through a resonance, and the frequency increases as well. Now, I'll show you how I use a modified form of Welch's method to calculate the PSD of rail roughness for a train that is varying its speed along the track. I split the track into 30-meter segments like this that are overlapped by 50% and map these segment boundaries onto the ABBA signal like this. I take the segments and apply a hand window to them like this, up to 30 segments. I then calculate the PSD periodograms of the ABBA segments and derive the roughness periodograms and translating them to wave number domain using this equation. The translation uses the average train speed in each segment, like this. Finally, I average together all the 30 periodograms, which gives me this spectrum. I can see that the derived spectrum is very close to the actual roughness, but the peak is smeared out. This smearing is caused by the assumption that the train speed is constant within each segment, but actually it is varying. So how do I reduce the smearing? So actually the smearing is coming from the first segment because that has the widest speed range. So I can reduce the smearing by removing this first segment. Now comparing the results with and without that first segment, you can see that has reduced the smearing. And I'll replot this as third octave spectra to see more of a real-world impact. I can see that the smearing is there's still too much smearing, so I will take another segment away and a third one. And now you can see that the derived roughness agrees with the actual roughness very closely. And I've used the segments that's at vehicle speeds above 5 meters per second, and I've only excluded 6 meters of track. Just to recap, I split the ABBA signal into segments according to vehicle position, excluding the data below 5 meters per second. I then calculate the periodograms of the segments translated them into roughness in the wave number domain using the average train speed, and I average the periodograms together and plot them in as a third octave spectrum. So far, we've assumed that we know the system exactly, but in reality, we don't have the exact transfer function for a real railway vehicle and track. But in reality, we don't, but we can approximate it using a model like this. Looking at the model, most of the parameters can be measured or calculated, but the track support stiffness and damping is probably the least known and most varying of the parameters. This is a problem that is perhaps blocking the widespread use of axial box accelerometers, as this idea has been around for at least 10 years. So we're developing a solution to this problem that identifies the track stiffness and damping using the P2 resonance in the ABBA spectrum. And this resonance is the wheel and rail masses vibrating on the track stiffness. So knowing the vehicle and rail parameters, we can derive the track stiffness from this, from the frequency and the width of this P2 resonance. Another problem we've tackled is that the wheel can have roughness as well as the rail, and both are added together in the ABBA signal. But we can separate the wheel and rail roughness spectra by averaging together portions of the ABBA signal over consecutive wheel revolutions. And this gives us the wheel component of ABBA, and the rail component is the signal minus the wheel component. Putting these through the roughness derivation techniques gives the separated wheel and rail roughness PSDs. To test this, I've simulated a combined wheel and rail roughness profile, and the green line is the actual wheel roughness, and the blue line is for the rail. And I'm going to add the results onto the same graph. This is the derived wheel roughness, and the red line is the rail. And you can see that they agree with the actual spectra very closely. To summarize, we are measuring rail roughness because it causes noise, vibration, and damage to the infrastructure as well. Axial box accelerometers can be a more cost-effective way of monitoring the condition of a rail network. And I've demonstrated a technique to derive the roughness spectrum from ABBA, given the transfer function and train speed. The track stiffness can be identified from the resonances in the ABBA spectrum. And I've discussed the trade-off in accuracy and resolution of the spectrum, and I've plotted my spectra according to this standard. I've shown that varying train speeds can cause smearing in the spectra, but if it excludes segments at vehicle speeds below 5 meters per second, then I can limit the smearing. Finally, I've demonstrated how wheel and rail roughness can be separated by cycle averaging, which is another issue with using axial box accelerometers. So far, we have tested these techniques in a simulated environment with a simple model of the train and track. Further work will scale up the track model and techniques to approach the behaviour of real track. Once we have achieved this, we will test the techniques with real data and compare them with existing methods of measuring rail roughness. The techniques go towards a wider goal of developing an autonomous monitoring system that maps the condition of a rail network using axial box accelerometers on passenger trains. It aids to track changes in the roughness of the sections of the rail network and enabling the rail operator to optimize maintenance schedules in order to control noise and vibration. And I'd like to express my gratitude to the EPSRC for funding this project and to West Midlands Metro for the opportunity to instrument one of their trams. And I hope I've inspired you with these techniques, which essentially derive the input of a system and parts of a system itself just from the output of a system. Thank you very much.